Damper.
An on-off point that where we are turning something on and off. Analog in, a temperature sensor. Okay, something that varies that we're reading. Analog out.
Modulate.
Bound. Program. Modulate.
Something that modulates, something that varies that we're controlling. Okay? So we use these terms all day long, so just make sure everybody keeps up with them. Starting with this air handler on these little sheets that I handed out. These will be some similar things that you saw on the other air handler. We're just going to change the rear end of the air handler, what would be up here on the picture up here. Okay? So, starting out here on the end, this is the supply air. This is our supply static pressure sensor. Okay, we're monitoring the static pressure of this device right here. And like you said last time, the actual sensor itself may be installed at our panel at the air handler, and then tubing ran out to some spot in the ductwork. And you'll see in this sequence of operation a little different scenario on how they're doing that one. What's this? Smoke detector. Okay, and the little note says that it's installed and wired by the fire alarm contractor. We put it on there just so we know that it's there. The engineer knows it's there, but control contractor is not actually going to touch that right there. Okay. What's this here? Temp sensor, measuring the supply air temperature, the dry bulb temp. Did y'all go through psychrometrics? Psychrometrics at all?
Way back when.
Way back when? Okay. So you know what I'm talking about between the difference between dry bulb or wet bulb temp? No. Okay. Well, real quick, dry bulb temp is just the temperature you would measure with a thermometer, and it's literally a dry thermometer, as opposed to a wet bulb temp. And they take a thermometer and put a wet wick around it and sling it around through the air. It gives you a different temperature. And you take those, that's called wet bulb. You take those two and compare them on a chart, and you can calculate the relative humidity. But we talk about temperature, and most times we're talking about dry bulb temps. Then right here, what's this?
High status.
High static pressure switch. Okay? It's going to kill the unit if the static pressure gets too high on the ductwork. Now on this one, you see they drew a little line here. This is they're showing a rooftop unit, and they're just saying that everything from this side over is below the roof. Everything on this side over from this direction to the left is on top of the roof. That's all that little line is. Supply fan, VFD. We have 3 points on this one. What are our 3 points usually?
On-off status. On-off status and speed.
Okay, we've got on-off, the enable point, approve, and then a analog out speed. And on this one, they didn't call for apparently a fault. Okay, so there's not a fourth point giving us the fault on this one. And then right here, what's this?
Mixed air temperature.
It's some kind of temperature sensor. I wouldn't really call that mixed air. Okay. It's just that's indicating this squiggly line for us indicates an averaging, as opposed to this over here indicates just a point sensor. Okay. And like I say, I'm going through this real fast. If y'all want to ask questions, ask questions. I don't know. Now, scooting back on the air handler, chill water coil, some kind of valve to control the flow of the chill water. And I don't know if we mentioned this last time, but where did we mount that chill water? On the supply return, the valve. Why do we do that? Darn, I was hoping somebody would tell me. It's always on the return, and the story I've always been told is just it keeps the pressure up in the coil.
It doesn't starve the coil.
Right.
You could have more suction on the return.
Okay, if we put it on the supply, we would tend to create not really create a vacuum, but be trying to pull the water. You'd have your pressure drop on the inlet side of the coil instead of on the downstream side of the coil. And so that just keeps the pressure up in the coil. What's this? Okay, and what's that do for us? Okay, if the coils get too cold, it's going to protect it. And what's it say here? So we're going to hardwire interlock, and I'll show you that wiring diagram here in a little bit. Plus, we're going to pick it up as a digital input. So not only is it going to automatically shut down the fan through a hardwired interlock, it's also going to tell the BAS that the freestat, I'm supposed to use that word, the low temp detector is tripped. Okay. Heating coil, heating valve, same thing. It's on the return side. These little symbols underneath here are just normally open, normally closed. Used to in the pneumatic days, that was critical that you got those straight because you might have just one signal going to both valves, and they had to sequence based on one being normally open, normally closed. With DDC, we can make them either way we want to. So that becomes a customer preference or an engineer's preference. Doesn't really matter to us in the DDC world whether it's normally open, normally closed.
How come we're getting away from three-way valve?
Just saving energy. I mean, two-way valves, we pinch down the flow. Three-way valve, the flow stays constant.
We're going to frequency.
Going to the VFDs on
VFD.
pumps. Yeah. Hey, there's no, on a three-way valve, you're talking, that's a constant volume system. You pump the same amount of, fluid through the system all day long.
But you gotta have at least one of them somewhere in the system.
Usually we have at least one, maybe two that are three-way, or we put a bypass, a little small bypass line at the end of the line, just to keep water flowing.
Is that you that does that, or is that the engineer that shows that?
Now, the engineer will have to show it, and yeah, because if he shows two-way valves on everything and doesn't show a bypass, that's exactly what he's going to get. Because you're not going to pick it up to pipe in a bypass. And if I handed you a three-way valve in lieu of a two-way, you'd probably get mad at me. But yeah, and there's several times we've had to go back and add them later. But mainly we do have to keep the water flowing so it's always hot or it's always chilled, whichever one. But also, let's see, I had in my head another reason. Well, a lot of times you can't go down below minimum flows on your pumps, and you don't want to back up the, if you can't, if the motor needs to have most of the motors have to run a certain speed to keep them cool, and so you're always going to be pumping some water, and if that amount of water would cause a pressure problem, then you can have a bypass to keep that from happening. But mainly for us, it's just to keep the water hot or cold. Okay, another temp sensor. This now is our mixed air temp sensor because we're mixing our return air from this path and our outside air from this path. So this is our averaging mixed air temp sensor.
Thomas, what would be the point of that TD5 mixed air temp?
This one right here. For me, just information.
Make sure
Make sure
the water's working like it needs to work.
Because what he's saying here is if we've got this temp sensor over here that we're going to control with, what's the purpose of this one? What would be the difference in these two?
increase temperature because of the fan.
Right. Okay. You can pick up 2-3 degrees of heat across the fan. And some customers, some engineers want to just be able to see that. Actually, on ours back here, we were seeing a 10-degree rise from this point over to this point. Okay? And we thought that was crazy.
So you got rid of one of the stats?
Do I?
So you got rid of one of the stats?
Yeah, we did one of them. We got it on the screen. Yesterday, just yesterday, when we started having trouble heating, we went up and looked. If you're looking down the ductwork, standing like at the inlet, the rear end of the air handler, looking at the chill water pool, they put the chill water coil in over here where the header is, and all the pipes, go into they didn't wipe that off. We had an opening that far. The only restriction in that opening was the header pipes. Okay, plus underneath the drain pan, the coil wasn't set all the way back on the back of the drain pan, so air is going through the drain pan. So we were bypassing a large amount of air. So they fixed that last time. That was our fault. So in that case, we had those temp sensors there and realized that that's got to be a problem. There's no way we're picking up 10 degrees of fan heat. Okay, filter, central pressure switch across the filter. Now, here's our added thing that we didn't have in the other air handler. This is showing a return air damper and outdoor air damper. Both of them have a motor on them, but they're both showing the same point on here. So that's just telling you the same signal's going to both actuators. But it's also showing this line right here that's dashed in the middle there is showing that they're mechanically linked. Okay? So one physically cannot open without the other one closing. Now, so what are we going to do with that? When it's cool outside, most all our air handlers are for cooling, so we're trying to maintain 55-degree air leaving the air handler. If it's below, what temperature outside would we start using outdoor air? What temperature would we want to start using outdoor air? If our return, what's our return air temp going to be?
75.
72-ish, 75, depending on what we're keeping our space at. So is it cheaper to use return air or outdoor air to supply the air handler?
Return.
Outside. If it's below.
Depends on what time of year it is. Okay, what would be the smart switchover point?
75, 72.
Why? Because that's probably what our return area is. Okay, so we have this other temp sensor up here on the return. We know what the return is all the time. We know what we're measuring the outdoor air. So we're going to compare the two. And if the outdoor air is cooler than the return air, we're going to say, okay, anytime that's the case, we're going to use outdoor air instead of return air. Okay, that's called just a simple dry bulb switchover to what we would call in the South our economizer mode. Okay?
Would you take 100% outside air at that time?
Well,
Or
think about it. If we say now we're going to use outdoor air, but what are we trying to maintain at the discharge? Down here we're trying to maintain 55. So this becomes our cooling now. So yes, it's going to go wide open.
And then I'm going to mess up the building pressure. Have a lot of outside air, you know what I'm saying?
Right here now, this is going to go closed. Okay? This now is going to take on a role of maintaining space pressure. So you're going to start relieving more air. So yes, that's a concern, but you take care of it, in another part of the sequence. Okay, so yeah, when we switch over at 72 or whatever that return air temperature is, it's probably going to go wide open. And it's not going to go below wide open until when?
get the blow. Freezing.
So we're mixing these two streams to maintain a temperature
55
here.
degrees.
Okay, so as we start going below 55 on our outside air, then this is going to start pinching down, and that'll open up, and we'll mix those two streams to maintain the discharge air temperature. Okay, so that's our mixing dampers. And again, we have an outside airflow station.
Are you going to be able to control humidity like that too?
Yeah, I mean, because you're still gonna be going through your chill water coil.
You're still gonna use the coil as the ring out.
Right, because if it's 60 degrees outside, even if it's 100% humidity outside, we're gonna take it in, it's gonna hit the chill water coil, we're gonna bring that down to 55 degrees. So we're still gonna be saturated leaving the chill water coil. And even in the heat of the summer, we're saturated leaving the chill water coil. So if that works during the summertime, yeah, it's gonna work during the wintertime or, the fall or spring also. Okay. Now, one thing that that people will do is they'll take the return air humidity that's right here and the return air dry bulb temp. Will calculate the enthalpy of the air, which is basically the heat content of the air. And then we'll compare that to we'll take the outdoor humidity and outdoor dry bulb, calculate the enthalpy of it, and switch over based on enthalpy. Okay. Sometimes that gives you a more energy efficient switch over instead of just a dry bulb alone. Okay. So now we've also thrown in a relief fan and a drive on it, and it's going to have another job to do. Okay, now let's start going through this, just to make sure everybody sees it. We also have our what over here? What is this?
Building pressure.
Okay, we've got a building pressure transmitter. We're measuring outside the building, and we're measuring inside the building, taking the difference between those, and we're going to probably maintain that. We'll read the sequence in a second. We're going to probably maintain that with that relief fan somehow or another. Okay? So, going through this sequence now. Occupied cooling mode, occupancy ventilation mode. And I read this a couple times and it just squirrely. But when the air handler is in the occupied mode, the fly fan shall operate continuously. Nothing fancy there. The frequency inverter, or VFD, as we would either like to call it, shall modulate to maintain the duct static pressure, and the cooling valve, heating valve, and economizer damper shall modulate the sequence to maintain the cooling discharge air temperature. Okay, this is just a summary of what the air handler is going to do. Discharge, okay. Discharge air. The outside airflow as measured at the air handling unit outdoor air intake. I need to look over here, I keep losing space. Shall be maintained at a value equal to or higher than the minimum required outdoor airflow set point. Determination of this minimum required outdoor airflow set point shall be per the minimum required outdoor airflow set point section of the air handler system level operation section of this specification. Okay?
You got
a lot
that?
of work.
You got all that?
A lot of words that just didn't say anything, okay? That was just a summary of what you're about to go through over here on the other side. Okay, when the air handler is in the unoccupied mode, supply fan is going to be off, the VFD is going to go to 0, outdoor air damper and cooling valve shall be closed, the heating valve shall be fully open. Okay, I personally, I'm going to close the heating valve, but if the sequence says open it, that's what I'm going to do. But that's, to me, that's more of a drawback to the pneumatic days, when you only had one signal going to them. If you close the chill water valve, the hot water valve opens up. Okay. Night setback. What is night setback or morning warm up? Can somebody tell me that real quick?
Unoccupied mode.
In the unoccupied mode, the night setback usually implies we're going to go to some room temperature. We're going to set it back and say where normally we might maintain 72 degrees in the space, we're going to try to maintain 60 degrees, let's say, or 55. That's our night setback temperature. Morning warm up. Since we've had the air handler off all night, we bring it on in the morning, and we try to do something with that air handler to quickly get the building, up to the temperature that we want it. So that's our morning warm-up cycle. This is what it's talking about here. When the HE is in night setback or morning warm-up heating mode, the supply fan shall operate continuously. The VFD shall modulate to maintain the duct static pressure. Outdoor air damper and cooling valve shall be closed. Okay? So at night setback mode or morning warm up, we're gonna keep that outdoor air damper closed regardless of the outdoor air temp. Okay? The return air damper shall be fully open, and the zone terminal reheats shall modulate to warm the building to the occupied temperature set point. So that's just talking about our VAV boxes are gonna go do their normal warm up. You know, we're gonna put them to an occupied mode, they're gonna open their dampers, and the reheat coils are gonna start, you know, the heat space up. Okay. All VAV terminal units shall enable local heat and operate in their VAV heating mode until the night setback morning warm-up criteria is satisfied and the HU returns to an occupied or unoccupied mode, depending on whether it's still nighttime or, you know. So there, we probably have some setting. We may even be looking at the return air temp and say we're going to go into morning warm-up until the return air temp gets to 70 degrees. Okay?
Are you gonna put a stage in there? I mean, you know, so where the valves don't have to hunt and search, I mean, run up to temp and then drop back down and run up to temp and drop back down to
What do you mean? Which valves?
the heating, the reheat valves?
The reheat valves?
Or the VAV box?
Well, the VAV boxes are going to,
Are they gonna be a constant air box?
now most of these are going to be VAV, and they're going to be at they're going to be in the heat mode because the building's cold.
Mm-hmm.
So they're going to go to whatever their heating CFM it should be. Now, that may be a varying heating CFM, which you're starting to do a lot of now, or it may be a constant volume. It just depends on the engineering. And it's going to go to that CFM, and then it's going to modulate the reheat valve to maintain the temperature on the wall, the space at. Okay. Any other questions on that? Now, at that point, it'll either be, if it was morning warm-up, we'll be switching to the occupied mode. If it was night setback, the air handler is just gonna go back down, the VAV box is gonna go back to, you know, an unoccupied setting. For night setback, we basically just bring the unit up to full speed for a while, heat the space back up to 60 degrees or something, you know, we pick some number, and then we let it go back on. Okay. Supply fan control. Supply fan shall operate continuously when air is used in occupied mode or in night setback or morning warm-up heating mode. The supply fan shall be off whenever the air is used in the unoccupied or the stop auto interlock is open, mixed air low limit is tripped, or the supply fan status in the case failure. This guy really liked to write a lot of stuff. Okay. Basically, when the air handler's on, the fan's gonna run. When the air handler's off, the fan's not gonna run. Next thing, the VFD, when it's on, it's gonna slowly ramp up and modulate to maintain the proper discharge duct static pressure set. Why do we ramp it up? Easier on the motor, belts, easier on the duct work. We don't get the little boom when the duct work, you know, fills with air. Energy. We don't get spikes. We may ramp it up over a minute, maybe 2 minutes. And basically all we do, we have a seconds counter and then a loop that's controlling static pressure. And both of those have an output, and the fan just runs to whichever one of those is the lowest. So it'll slowly, the loop output is going to be calling for full speed because there's no static pressure. The seconds counter is going to start at 0, so it's going to come up, the fan's going to slowly ramp up until those two meet. Seconds counter going up to full output, and then the loop will sit there and modulate the fan from then on. Okay. Okay, we kind of talked about the economizer control already, but it says here that if it's less than the changeover set point, and we discussed how you come up with that set point, then the outdoor air damper shall modulate the airflow between the minimum required outdoor airflow set point and a full open position to maintain the discharge air temperature. So on this one, if we're using outdoor air, it's going to modulate this outdoor air damper to maintain the supply air temperature. okay? Instead of maintaining this one, the mixed air temp, it says that it wants to actually maintain the discharge air temperature set point. Okay, so that's going to be in sequence with the chill water valve. You don't want both of them working. Until that outdoor air damper gets wide open, then the chill water valve would open up. Okay. Now, it keeps saying below to maintain some CFM between the minimum required. So we're always measuring our outdoor airflow, and we're not going to pinch the outdoor air damper down below that minimum airflow. Okay, so if we get down to where this is maintaining a minimum flow here and it's still too cold, that's when we'll start using the heating valve to bring that discharge air temperature back up. Any questions there? Talks about also that this low temp detector is going to be a manual reset. Talks about a bunch of stuff in here about if different temperature sensors have failed, what we do, and that's really confusing. That's getting into a lot of detail that we usually don't see. But it says stuff like if this temperature sensor fails right here, then we go to just an airflow control over here. Just go to a minimum. Whatever. If the supply air temp sensor fails, we do something different. If we have time, we'll go back and go into that in detail. We'll skip that for right now.
Tom, that mixed air temperature sensor after your cooling coil, it's
Right.
that's just a monitoring point. It's not providing any kind of temperature for feedback for the valves or anything like that.
Not really. Yeah, it says here the heating valve control that is kind of, if the mixed air temperature is below the discharge air cooling set point and the outside air damper is at minimum, then the heating valve shall modulate to maintain the mixed air temperature at the discharge air set point. That's a typo there because this is your mixed air temperature. And so that cooling coil, that heating coil cannot modulate to maintain the mixed air temperature. It should be the supply air temperature. And it says something about a heating SCR, so I don't know if that SCR is a typo or if this really is electric heat. Okay, SCR is talking about modulating electric heat strip. That looks like a typo also. Says that the heating shall be disabled when the outdoor airflow rate exceeds the required minimum airflow set point by more than 10%. Okay, all he's saying is that if we're above our minimum airflow, then we don't want to use heat. Okay, he's just trying to make sure that we back the damper down to that minimum before we actually use any heat out of the coil. That's all he's saying by that right there. Cooling valve. Cooling valve shall modulate to maintain discharge air temperature at the discharge cooling set point. If the economizer function is enabled and the outdoor air damper is not fully open, the cooling valve shall be closed. Again, all he's saying is that if this damper is not fully open, I don't want to be doing any mechanical cooling. Okay? Make sure that this is in the sequence. Make sure that this damper, the outdoor air damper, is wide open before we start using the chill water coil.
Why don't they make it that easy and just say that?
Matt printed this out for me yesterday, and I was sitting there reading
Well, I
it.
mean-
Golly.
Because the lawyer wrote this up.
No, you look at what building this is, and that probably makes it. That's the engineering building, so that probably helps.
Yeah, there's a lot of verbiage in here. The minimum required outdoor airflow set point. So now we've talked about this airflow station, and now we're going to talk about how do we come up with how much air to bring in here. In the past, what would we do? We just open and close that outdoor air damper. Then we started saying, we need some fresh air in the building all the time. So what did we set for fresh air in the past? we just arbitrarily picked a number, or we had the balance guy measure the outdoor airflow and tell us, okay, that's good, and whatever that position was on that outdoor air damper, that was our minimum. We wouldn't go below that. Well, with VAV, that worked okay on constant volume units. With VAV units, that don't work. Okay? And with more people concerned about the exact amounts of outdoor air we're bringing in, we're being forced to measure it.
Yeah, I mean, we had talked about that before, regulation-wise, years ago. I mean, how many times has that minimum changed? I mean.
Oh, yeah. It keeps creeping up.
Yeah, I mean, it used to be 10%, and then it just keeps getting more and more and more.
But, you know, nowadays, and now with the, is it standard 60? I think it's standard 62 hash rate, yeah, 62.99. They're wanting, you know, we've got to actually come up with a way to either count the number of people in a space or use something like CO2 measuring and, you know, vary that outdoor air, you know, to try to bring in just the right amount of outdoor air for the number of people that are in space. Now, what it talks about here, and I'll try to read this where it makes some sense. The outdoor air dampers shall be controlled to deliver the required outdoor airflow to each individual VAV zone at all load conditions. So, right, two things that happen. You got VAV boxes that are varying how much air they're putting in a zone. And you got the air handler that's varying how much air it's pushing down the ductwork. Okay? The minimum outdoor airflow set point shall be determined using ASHRAE standard 62-99 equation 6.1. The actual outdoor airflow shall be sensed at the outdoor air intake, that's our airflow station, right here. Okay? The ventilation fraction, and it says here that's the design ventilation airflow for the zone divided by the primary airflow, shall be continuously calculated for each VAV terminal zone. Continuously determine the maximum zone ventilation fraction, the sum of the outdoor air requirements for all VAV zones, and the total supply airflow. This information shall be used in equation 6.1 of ASHRAE standard 62 to calculate the minimum required outdoor airflow.
That damper's never gonna be still.
That's why it says you gotta continuously calculate it. Okay, so you've got a VAV, can everybody see if I go right here? Make it good something. Quick and dirty. We got a VAV box that modulates between, let's say, 100 CFM up to 1,000 CFM. Okay? So at full load, it's at 1,000. At minimum load, it's at 100 CFM. How many people we have in the space? I don't know. We got 5 people in there. 5 people need a certain number of CFM for fresh air. I'm guessing here, I don't know these numbers. Steve will know these numbers off the top of his head. But let's say that whatever it is, that 5 times that amount comes up to this 100 CFM, just for calculation purposes. Okay, so I need 100 CFM in this room, this one room, out of hundreds that this air handler may be serving. I need 100 CFM of fresh air in this space. So if I'm down at 100 CFM, what percentage of outside air do I need in that space? 100%. So what fraction of outside air am I going to have on do I need in my air handler? Okay? When I start measuring, we'll find that clip. When I start measuring here, and I've got, say, 10,000 CFM leaving the air handler, how much outside air do I need to give me 100% of fresh air in this one room? If you didn't take any of the diversity or return air into account, you would have to have 100% outside air coming from that air handler to satisfy the fresh air requirements in that one room. Okay? But what ASHRAE, that equation 6.1 says that that's never going to happen. We're not going to bring in 100% fresh air from that air handler to satisfy that one room. For one, you've got other spaces that probably don't have people in them. And that return air gets to count as fresh air. Okay, so they came up with this big convoluted equation that takes all that into account and wrote this equation, and we can use it. And what we do is we take whatever fraction this comes up to, that fraction goes into another equation, and that always continuously during the day gives us our outdoor air fraction that we need here. So if that comes up to 50%, and we're supplying 50, say, are we even measuring that over here? We don't have an airflow station on the supply plan, do we? Darn. Well, if we were supplying 5,000 CFM of air and we needed 50%, then we need to bring in 2,500 CFM of outdoor air. Okay? So this big convoluted paragraph here just tells us how to calculate how much fresh air to bring in here. So that will become our minimum. We can go above that, but we can't go below that. Okay? Now, let's jump real quick. The rest of this sequence on this other page talks about discharge air pressure set point. We went through that pretty good last time. And then building static just says that we're going to modulate that relief fan. We're going to always monitor the building pressure, and we're going to modulate this relief fan right here to maintain our building pressure. As the pressure in the building increases, we'll speed this fan up. As the pressure in the building decreases, we'll slow it down. Okay? And that fan right there is pulling out of this mixing chamber and blowing straight outside. Okay? So that's our pressure, building pressure control device. Let me jump to, let's see. Is that it? Yeah, that's it.
We opened up a can of worms.
Okay, this is a wiring diagram for this air handler. And I want to show some of these devices that we talked about and the difference between hard wiring and bring them into the BAS system. Right here shows our VFD on the supply pin. This is some kind of relay. Now, right here at the top, we're showing safety terminals, safety interlock terminals on the drive. That's a set of terminals on the drive dedicated to some kind of safety switch. Below it, we've got a set of terminals for a start-stop. This says if whatever is connected, whether it's dry contact or whatever, maybe it's even jumpers, we don't know. But if that's closed across there, then that says this drive, we're wanting this drive to run. Here's our speed input, probably a 0-10 volt. Here's an output for a fault, we're not using it. And then here's an output for a status, a digital input back to us. So let's look at this safety circuit right here. We come up here and we notice that it's wired through the normally open contacts on this relay. Okay, so immediately we know that this relay coil right here has to be energized for that circuit to be made and the safeties to be in a safe condition. Okay? If that relay de-energizes, we break that circuit, drive's going to shut down. Now, let's trace back and see what all has to be made to get this coil to energize. Okay, so we come back here. We see here that it's tied into the coil of the relief fan also, so let's just ignore that side. So we come back here, it goes to a terminal, comes out here, and what's this? Fire alarm interlock. That's some relay that the fire alarm contactor has brought over and set next to our panel. We're going to wire through it. Okay? We go back here to the terminal, jumpers. What's this right here? If you look back on your drawing, that low temp detector there between the heating coil and the cooling coil is labeled LTDE1. That's the normally closed contact. That's actually, I'm not being drawn on, but that's showing a normally closed contact on that low temp detector. So that has to be satisfied. So our current now can come on through here, goes through these terminals, back out here. What's this? This is our high static pressure switch on the discharge of the unit. So this has to be satisfied. Okay, so we come back here, and what is this? This is our hot side of our transformer. So we got hot, power comes down here. As long as the deep differential pressure switch is satisfied, we can go through it. We can continue up here. As long as the low temp detector is not tripped, we can get through there. As long as the fire alarm's not in an unsafe condition, we can go through there. Come up here, we put power on our coil, go back to common. That coil will pull in, and our safety circuit is made. Now, this is what he was talking about last Thursday. This is called being series through these safeties. Okay, if any one of those breaks, we lose our power to that relay, the relay contacts open up, drive shuts down. That's what we're talking about on a hardwired interlock. Our panel could be, it lost its brains, somebody be monkeying with it and turn stuff on manually. Either way, it's still going to shut down that drive. Kill it. Okay? That's our hardwired series interlock. Now, you see here the low temp detector has this other set of wires on it. What do you think that is?
Yeah.
Okay? If you look over on the other side now, you see that at the same time that opens up to kill the circuit, this is going to make and go over here to a point in our BAS system called the low temp detector. So that we'll know immediately that that was the low temp detector that tripped. Okay? A lot of times we'll do the same thing with the different pressure switch. They didn't do that on this one. They didn't call for that. We might even do the same thing with the fire alarm. Just depends on what the engineer called for. But on this one, the only one we have proof of is the low temp detector. So this is software, a point coming into us as an input, as opposed to hardwire interlocks that go to the drive. If we're supposed to be done at 7:45, we're at 7:45. Or should what? Keep going. Okay. But that's the hardwired interlock. And then the rest of this down here, if you see, they just did the same thing for the relief fan. All those safeties will shut down both the relief and the supply fan at the same time. Okay? We have the same stuff over here for the relief fan. We've got enable, a speed output, and a proof input to us. And this is just a ladder type diagram showing our guys what points to pick up, what to hardwire on this air handler. Keep going down. Here's our mixed air damper output point. Probably a 0 to 10 volt. It's wired over here in parallel with both of these motors. These are our two, that's our outdoor air damper and return air damper motors. And then of course both of those have to have 24 volt power to them, so that's what that's showing there. Okay. Same thing with our cooling coil and our heating coil valves. An analog output going over to the cooling valve. Analog output, probably 0 to 10, going to the heating valve. And then both of them require 24 volt AC each one of them. Here is just a quick and dirty differential pressure switch on the filter. If that pressure gets too high, it closes that contact. We get a digital input to us making an alarm.
This is all in one panel.
The way this drawing works, if you look up at the top, it's divided into 4 sections. On the far left over here is the field panel. That's our controller, like one of these devices sitting on the desk here. We call it MEC. Okay, all of these points are wired back to that MEC panel, probably one controller panel. Then this next section, where we have this transformer and some terminals shown, will be some kind of component panel we'll mount next to it. We'll either call it auxiliary panel, component panel, equipment panel, whatever the term. And we'll mount some relays in there, just mount different auxiliary devices that are not part of the controller. Okay. Then the next section is showing the actual field wiring that goes between a panel and out to the air handler. And then this last section is showing the starter, or in this case, the VFD. That relay, by virtue of being under this category, it tells me that that relay is mounted in the VFD, or in this case, located near VFD. Okay, so that gives us 4 different sections to tell the guys, that this should be mounted here, this should be mounted there. If you notice, all your temp sensors, low temp detector, those kind of things are showing out here in the field, which, is part of the air handler. Keep that other thing that I handed out with the V&E boxes on it. Probably going to start with that on next time. We will have this set up in here on Thursday morning also, so you'll have to deal with this on Thursday morning also. But
That's the training session.
other than that, I guess I'm done.